All right, so this is going to be an example problem of integration using partial fractions, and this one's kind of tricky. It's kind of why I wanted to make a video of it. It helps with these tricky ones to kind of see what you're supposed to do and why what we would normally do might not make 100% sense, so you kind of have to change the rules, bend the rules anyway, at least a little bit. First thing that I would do is see if anything could simplify here, which you can see that it doesn't. So I'm going to start with making my partial fractions. Now you might be tempted to do the following. You might be tempted to do this because it's similar to what we've done before. This bottom part is already factored, so that makes it nice, and then you just use partial fractions and you divide it up using whatever that denominator is. However, when it's a perfect square like this, you kind of have to change the rules a little bit, and I'm going to show you why. If we actually worked this all the way out, this would be equal to, because it's common denominators up there, a plus b over x plus 3. All right, and there's no way that this could possibly represent this up here because it's not even squared on the bottom, okay? It kind of throws a wrench into the whole process of doing this, and it's just not going to work, long story short. So what we're going to have to do is bend the rules a little bit. Now to bend these rules, what we're going to do is whenever it's a perfect square, perfect cube, or perfect anything on the bottom with those factors, we are just going to match the denominator with whatever the second term is. In fact, the rule is just raise the first one to the first power, the second one to the second power until you get to that 2. So if that was a 3, we'd have to go another one with x plus 3 quantity cubed. So there would be another term here, but this one just has 2. So we're just going to leave it like that. That's basically the rule that you're going to want to use. And this still is going to work out because our denominator actually matches with what we start with. And we still end up with finding that a and b. It just doesn't work if you break it down and don't square it or don't put it to whatever power is right here. So that's basically the little trick. All right, so we're going to simplify this here, and it's going to be a times ln of the absolute value of x plus 3 plus b. Now this is going to be x plus 3 to the negative 2 power, so you have to add 1 to that power. So it's going to be negative 1, and then divide by whatever that power is. You end up with something like that. But we do need to figure out what a and b are because we have to solve for them here and here. So to do that, we're going to set up our equivalent statement for this fraction that we were breaking down using partial fraction decomposition. All right, from here, I'm going to multiply both sides by that x plus 3 quantity squared. And the reason I do this is because it gets rid of all the fractions. So that's gone on that side. And then I'm going to distribute this to this first term here. So you end up with 5x being equal to a times x plus 3, since one of them cancels with this bottom one, plus b, because when you distribute this to here, the x plus 3 quantity squared is just going to cancel. You end up with b. The rest is just basic algebra. You end up with ax plus 3a plus b. Okay, looking at this, you should see that a is going to be equal to 5, and 3a plus b is going to be equal to 0. Well, we know that a is equal to 5, so that would be this make this 15. So that means b is equal to negative 15. All right, so now we're going to rewrite this orange part right here, and it's going to be a is 5, so it's going to be ln. So we solve for this a right here. 5 ln x plus 3. So that's this term right here. Plus, now we know what b is because it's negative 15. So it's negative 15 over negative 1. That's just going to be 15. And it's times x plus 3 to the negative 1 power. So I'm just going to divide it by x plus 3. It's the equivalent statement, and then you still need the plus c, and that is the final answer for that problem. So that's a kind of tricky integration problem using partial fractions. And again, the main trick is if you have that perfect square, perfect cube, or perfect whatever on the bottom, then you're going to need to make sure that you break down that partial fraction based on what we did right here. You're just basically going up each thing you're adding until you get to that power, which is 2 here. So we went from power of 1 to a power of 2. So that's basically a problem with integration using partial fractions. If you have any questions about anything in this video, let me know.